Hello everyone, my name is Bobbi Yogatama, and I'm a PhD student from University of Wisconsin-Madison. In this presentation, I'm going to present our work on tile-based lightweight integer compression in GPU. This is the work that I'm doing with my advisor, Professor Xiangyao from University of Wisconsin-Madison, and our collaborators, Anil Shanbhag and Professor Madden from MIT. Recently, GPU has been increasingly more popular for applications such as data analytics. This is because GPU has several advantages over CPU. The first advantage is that GPU has a much higher computation power since it has a massively parallel cores. For applications that are easy to parallelize, such as data analytics, this can provide significant benefits. The second advantage is that GPU has a much higher memory bandwidth. Modern GPU can have up to 10 times higher memory bandwidth compared to CPU. Therefore, for memory-bound applications such as data analytics, this can provide massive speedup. Previous work actually has shown that it is possible to saturate the GPU memory bandwidth when running data analytics, which can lead to 10 to 25 times speedup over CPU. Unfortunately, these advantages also come with some challenges. The first challenge is that GPU has a limited memory capacity. Modern GPU nowadays only have up to 80 gigabytes of device memory. Therefore, some of our data set might not fit in the GPU memory. It is always possible to transfer the data from CPU. However, the interconnect bandwidth between CPU and GPU is also limited. Most of the GPU nowadays still use PCIe Gen 3 as its interconnect, which only has about 12 gigabytes per second of bandwidth, which is why transferring data from CPU to GPU can be quite expensive. The goal of this work is to actually solve these challenges by using data compression in GPU. First of all, we will see the roadmap of GPU database, and we will show how our work could fit into the picture. In this figure, the x-axis is the data size in gigabytes, and the y-axis is the throughput in terms of data processed in gigabyte per second. We can see that the throughput line for CPU is going to be flat until it hits the CPU memory capacity of 100 gigabytes to 10 terabytes. For GPU, the throughput line is going to be much higher since GPU has a much higher memory bandwidth. But the line is going to be shorter since the GPU memory capacity is quite limited. And therefore, beyond this point, the performance will drop significantly since the data has to be transferred from CPU to GPU. Our goal here is to actually extend the inflection point as further as possible by using data compression, since it can enable us to fit in more data in GPU memory. Data compression will also be able to reduce data transfer cost from CPU to GPU, since we can transfer the compressed data instead of the original data. In this work, we will focus on integer data types, since other data types such as string is often dictionary encoded to integer in GPU database. We will also be focusing on decompression rather than compression, since decompression is a recurring activity, whereas compression is a one-time activity. For example, we will have to decompress the data every time we launch the query, but for compression, we only need to compress the data in the beginning and store it in the global memory. Therefore, the goal of this work is to optimize the compression performance such that it is not a performance bottleneck in query execution. After doing some investigations, we actually identify two limitations in existing GPU data decompression scheme. The first limitation is that decompressing a cascading compression scheme is slow. Cascading compression scheme is multiple compression scheme that is layered on top of each other. For example, we can have a bitpack encoding on top of delta encoding, which results in cascading scheme of delta plus bitpacking. Decompressing this scheme is slow since it requires multiple round trips to the GPU memory, as we will show in the next slides. The second limitation is we found that existing bitpacking scheme in GPU is still inefficient and it does not saturate the GPU memory bandwidth. Bitpacking is one of the most widely used lightweight compression scheme, and therefore we think it is important to optimize this scheme in the context of GPU. We will show in the next few slides how we address these two limitations in our work. The first limitation that we want to address is cascading decompression. Our solution here is to introduce a new decompression model, which we call the tile-based decompression. We will show with a running example the difference between conventional decompression model and tile-based decompression model. In this example, we are decoding a cascading compression scheme of delta plus bitpacking and then launch the query. In conventional decompression model, we will first launch the first kernel to decompress bitpacking. This would require us to read the compressed data from the global memory, decompress bitpacking, and write the result to the global memory. After that, we would launch the second kernel to decompress the delta scheme. This would once again require us to read the intermediate result from the global memory, decompress the delta, and write the results to the global memory. After this, we have finished the decompression of the whole scheme, and finally, we can launch the query kernel on the uncompressed data by having another round trips to the global memory. We can see that this is inefficient since it requires multiple round trips to the global memory. We will now show how to decompress this scheme in our proposed approach. In tile-based decompression, the first step is the same, which is reading from the global memory and decompress bitpacking scheme. However, instead of storing the result to the global memory, we will store the result to the shared memory instead. This will allow the next step, which is delta decoding, to read the intermediate result directly from the shared memory, decompress the delta, and store the result once again to the shared memory. The decompression step of these two schemes can now be performed in the same kernel. Even better, we can encapsulate these multiple decompression steps into a single CUDA device function and call it from within the query kernel. As a result, the query kernel can run on top of compressed data, decompress the data on the fly, and read the decompressed data from the shared memory. This model is more efficient since it only requires a single round trips to the global memory to decompress the whole scheme and execute the query. One requirement of tile-based decompression is that the intermediate result has to fit in the shared memory. In order to do this, we partition the data into tiles, where each tile must fit in the shared memory. For our scheme, we use a tile size of 512 integers. During compression in CPU, we will compress each tile independently, such that each tile can also be decompressed independently. During decompression in GPU, we will have each thread block in the GPU to decompress each tile independently by interfacing with the shared memory. This would allow us to enable tile-based decompression model. The second limitation that we want to address is we found that existing bitpacking schemes in GPU are not efficient, and therefore our solution is to introduce an efficient bitpacking scheme for GPU. Our bitpacking scheme has a compact data format which is built on top of tile-based decompression model. We also introduce some low-level performance optimizations and show how our bit packing scheme could saturate the GPU memory bandwidth during decompression. We name our bit packing scheme GPU4, which is basically frame of reference plus bit packing. We show the data format of our scheme in this slide. We can see that the data format is divided into blocks since we built our scheme on top of tile-based decompression model, which we explained in the previous slide. The details about this scheme and its optimization are going to be omitted from the talk and explained further in our paper. To show the versatility of our data format and to show how tile-based decompression model can be adopted by other schemes, we also introduce two other bit packing schemes, which is GPU D4 and GPU R4. GPU D4 is delta plus GPU 4, whereas GPU R4 is RLE plus GPU 4. We also show that with slight adjustment to GPU 4 data format, we can build the data format of other bit packing schemes. Even though we just showed two examples, it is also possible to adopt this model to other and even more complex cascading scheme. In the next slide, we will show how our scheme perform against existing compression schemes in GPU. In our evaluation, we use NVIDIA V100 with 16 gigabytes of high bandwidth memory. For our benchmark, we use star schema benchmark with a scale factor of 20. The string column in star schema benchmark will be dictionary encoded into integers before stored in GPU. The total dataset size is around 13 gigabytes, which will completely fit in the GPU memory. In this experiment, we are showing the compressed data size for each column in star schema benchmark. We can see that our design, which is GPU star, is comparable and even slightly better to the best previous scheme, such as NVCOM. NVCOM is a native CUDA-based compression library developed by NVIDIA. GPU star and NVCOM support the same variety of lightweight compression scheme, which is delta, RLE, and bit packing. We can also see that our design could reduce the total memory footprint by 2.8 times. In this experiment, we are showing the performance of running star schema benchmark queries on various compression scheme. Our design is shown to be performing very well and is 2.6 times faster than best previous scheme. This is because for other schemes, we will have to decompress the column one by one before actually launching the query kernels. Whereas for our scheme, the tile-based decompression model will allow us to perform multiple decompression steps in a single kernel and in line with the query execution, resulting in significant performance benefit. Compared to running on uncompressed data, our scheme is only 1.35 times slower, where the overhead is coming from extra operations of decompressing the data during query execution. We also conduct a more detailed experiment with various data distribution that can be found in our paper. To conclude our presentation, we can see that data decompression could help mitigate the limited GPU memory capacity and also reduce the data transfer cost. The main challenge of data compression is existing decompression scheme is still inefficient. Therefore, in this work, we provide two solutions to optimize decompression in GPU. The first one is we introduce tile-based decompression model, and the second one is we introduce efficient bit packing schemes. We then show in our evaluation that our scheme is 2.6 times faster than the best previous scheme in query running time. Therefore, this concludes the end of our presentation. Thank you very much for your attention, and I'm happy to answer any of your questions. Thank you.